This is section 8.5, Properties of Logarithms. Our objective today is I can use properties of logs to approximate and solve logarithmic equations. So just looking at some basic logs under a little discovery. When we evaluate log 2 of 2, we would end up getting 1. When we would evaluate log 3 of 3, we would end up getting 1. When we evaluate log 4 of 4, we would end up getting 1. Now, if you need to see why this is going to be the case, I'll just take that last example we just did, log 4 of 4, and work that out down at the bottom. So if we have log 4 of 4, based off of what we've done in previous sections, we would set that equal to x. And then we would rewrite this in exponential form. So 4 to what power gives me 4. 4 to the power of x equals 4. And we know that 4 to the first power gives us 4. So x equals 1. That's why we get 1 on all of those. So if we take a look at the next example, log 5 of 5 to the third, we could rewrite this. And if we have log 5 of 5 cubed, we could set that equal to x. And then we could rewrite that as 5 to the power of x equals 5 to the power of 3. Well, in order to make those be the same, we'd have to say, okay, x equals 3. So when we evaluate, we would get 3. Now, if you notice, something that's really interesting about these is that our answer is always going to be the exponent of whatever our large number is. So in the first example, the 2 could have been raised to a power of 1. Then the 3 would have been raised to a power of 1 if we were to give it an exponent. Then the 4 would be raised to a power of 1 if we were to give it an exponent. And then here, the 5 already has an exponent of 3, and you can see that 3 is our answer. So here, without even solving this, we can already know that our answer is going to be 4. And this is only the case when the small number and the base match up. So here we have 2 and 2. Here we have 3 and 3. Here 4 and 4, 5 and 5, 7 and 7. This isn't going to work out if those numbers don't match, but since they do, we can use that property. So when we have log x of x to the power of y, our answer is going to be what the exponent is, which in this case is y. Some properties that we're going to be looking at is the product property, quotient property, and power property. So looking at what these actually mean, when we're looking at the product property, we have two things that are being added together. They have that same small number, but they have different bases. So we have log x of a plus log x of b. And we can go back and forth between addition and multiplication when we're talking about logs. So if I wanted to write this as one log, which you will have to do sometimes, you would write log x of a times b. And that would be writing it as one log. We can combine those since they have that same small number and write it as log x of a times b. Similarly, with the quotient property, we can go back and forth from subtraction to division, division to subtraction. So here, if I were going to write it as one log, I would write log x, and then whatever the first number or letter is going to be first, and it's actually going to be division, so we're going to have a over b. And then we have the power property of logs, and what that means is if I have something in the front, so example, there's a p in the front of this log, we can move that and make him an exponent. So we would actually write this, if we were going to be doing that, as log b of m to the power of p. And these are properties that we're going to be using to actually approximate and solve logarithmic equations today. In example 1, we're going to be using the product property. So it's really nice that they go ahead and tell us what we're going to be using. They gave us log 4 of 3 is approximately 0.7925. So we know that we're going to end up using that. Okay, we're going to end up using log 4 of 3 in some way. So we have the equation log 4 of 12 that they want us to be using. So if we take this problem and we know we have to change it into log 4 of 3 because that's what they gave us. Okay, so we're going to go ahead and write this as log 4 of 3, but I can't just change by 12 to a 3. So I'm going to change it to 3 times 4. And that way it doesn't change the value of what I'm doing. Okay, so using that product property, I know if I'm multiplying two things, I can rewrite that as an addition problem. So I have log 4 of 3 plus log 4 of 4. And based off of what they gave log 4 of 3, I can go ahead and say that this equals, the first part is going to be 0.7925 because that's what they gave me. That's this. Then, for log 4 of 4, just like with what we were doing at the beginning, we know that that's going to give us 1. So now we can add those two together to get our final answer of 1.7925. On example B, it's very similar to the first example. We need to figure out how can we rewrite this. So I have log 4, and they want us to find 32, but they gave us 2, so we want to figure out, okay, how can I write this? So 32 divided by 2 is going to give us 16, so we can actually write this as 2 times 16. Now let's figure out why that's going to help us out. So we can rewrite this now using our product property as an addition problem. So log 4 of 2 plus log 4 of 16. And we know that that first equation, we know what that equals because they gave it to us. So I'm going to go ahead and fill that in as 0.5. And then we still have this log 4 of 16 that we're dealing with. And what we can do here, we can change this 16 into a 4, because remember we want this to match the base. We want the small number to match the base. So we're going to have 0.5 plus log 4 of 4 squared. And then going back to that very interesting property we looked at the beginning, we know that since these match and it's squared, then the answer here is going to be 2. So we end up with 0.5 plus 2, which gives us 2.5 as our final answer. In example C, we'll be doing the same type of deal. It is addition, so first we're going to actually be changing it into multiplication. So here we're going to have log 6 of x times x minus 9, and that's going to equal 2. Okay, so now I can do a little bit of simplifying. I'm just going to distribute first. And that's going to give me log 6 of x squared minus 9x equals 2. And then rewriting this as an exponential equation, we know that 6 squared is equal to x squared minus 9x. 6 squared is 36. And then we want to go ahead and move everything over to one side. So I'm going to subtract 36. And I'm going to be left with x squared minus 9x minus 36 equals 0. And now I can just factor using big X to solve this. So in big X, I'm going to have negative 36 on top. I'm going to have negative 9 on the bottom. So my numbers are going to end up being negative 12 and 3, because negative 12 times 3 is negative 36, and negative 12 plus 3 is negative 9. So we have x minus 12 and x plus 3. And so my final answers are going to be x equals 12 and x equals negative 3. And we will need to check these answers since there's 2 of them. So since we got 2, we're going to plug them back in And we're going to end up with, when we're talking about the -3, we're going to end up with log 6 of -3 and log 6 of -12. And those are going to be undefined. So x equals -3 is actually not a solution. It's extraneous. So our only answer here is x equals 12. And I'm actually not going to go through example D because it's the exact same as example C. So you can try that on your own if you need some extra practice. In example 2, we're going to be using the quotient property. So on A, it says that log 4 3 equals 0.7925 and log 4 of 5 equals 1.1610. We're going to use that information to approximate the value of log 4 of 5 over 3. So first, I can go ahead and take that equation, log 4 of 5 over 3, and expand that out. And I'm going to expand that to log 4 of 5 minus log 4 of 3. So I'm using that quotient property to take division to subtraction. And I'm trying to find out what this equals. So now I can go ahead and plug in the values that they gave me. They said that log 4 of 5 was equal to 1.1610. And I'm going to be subtracting log 4 of 3, which they gave me as 0.7925. So now this is just a very simple subtraction problem. 1.1610 minus 0.7925, and that's going to give me, for my final answer, 0.3685. On example B, it's very similar, same type of problem. We have some information they're giving us. They want us to approximate the value of log 4 of 3 over 4. So I'm going to go ahead and expand that out. So I'm going to have log 4 of 3 minus log 4 of 4. So then I want to check what were those values. Well, I know that log 4 of 3 was 0.7925, and I know that log 4, oh, and actually this is a typo here. This should say log 4 of 4 is what they gave you, of 1.1610. So now that I have that, I have minus 1.1610. So I'm going to, again, just do a very simple subtraction problem. 0.7925 minus 1.1610, and that's going to give me negative 0.3685 as my final answer. And then we get into C and D, and we have a subtraction problem. So now we're going to actually be moving to division. So on the first example, we have log 3, 56, minus log 3 of n equals log 3 of 7. So on the left-hand side, I can go ahead and combine this into one log. So I can have log 3 of 56 over n equals log 3 of 7. And we don't want to forget all of our properties that we've learned before. So looking at this, we know that since they both have a log 3 on each side, we can go ahead and we can get rid of those log 3's so that we're just left with 56 over n equals 7. And so I ask myself, 56 divided by what equals 7? And so if I take 56 and I divide it by 8, it's going to give me 7, which means my final answer is going to be n equals 8. Example D, very, very similar. We'll go ahead and rewrite it as one log. So we have log 4 of 48 over n equals log 4 of 6. Again, my bases are the same, so I can cancel those out. So I have 48 over n equals 6. And so I ask myself, okay, 48 divided by what is going to give me that 6? And I know that 48 divided by 8 is going to give me 6, so actually n is going to be 8 again in this case. It won't always be 8, it just happened to work out this way in these problems. In example 3, we're going to use the power property to solve for the logs. So it says we have log 2 of 5 equals 2.3219, and they want us to approximate the value of log 2 of 25. So we know we want to take log 2 of 25 and write this as log 2 of 5 because that's what we have to work with. So if I were going to write it that way, I could have log 2 of 5 squared, because 5 squared equals 25. Remember, we can't just change the value and write 5. It still has to be equivalent to the 25. And then using that power property, I'm going to move that 2 up to the front so that I have 2 times log 2 of 5. And since log 2 of 5 is 2.3219, I can plug that in for the log part and then just multiply it by that 2 that's in the front, and then it's just a very simple multiplication problem. 2 times 2.3219, which is going to give me 4.6438 as my final answer. In example B, it's going to be the exact same type of thing. We're going to take this log 349. We want to change that to log 3 of 7 because that's what they gave us. So we're going to put log 3 of 7 squared because 7 squared will give us the 49. We're going to move the 2 to the front using that power property. So we have 2 times log 3 of 7. And we know log 3 of 7 because they gave it to us. We're going to keep our 2 and we're going to plug in that log 3 of 7, which is 1.7712. And then it's just a very simple multiplication problem. We're going to have 2 times 1.7712, which gives us 3.5424 as the final answer. In example C, we are looking at a couple of different properties we're going to be using actually. So first, I'm going to go ahead and use the product property to move my 2 so that I have log 7 of x squared. And then on the right hand side, I'm going to go ahead and change it to log 7 of 27 times 3 because we know that addition can go to multiplication. And 27 times 3 is going to give us 81. So we use a couple of different properties here. Now that my bases are the same, or my logs are the exact same, I can go ahead and get rid of those. So now I have x squared equals 81. So I'm going to take the square root of both sides, and I'm going to end up with x equals 9. And then for that last example, we're going to go ahead and move the 5 to the x, so we have log 2 of x to the 5th equals log 2 of 32. And since I have log 2 on both sides, those are going to be gone. I'm going to end up with x to the 5th equals 32. And I'm going to take the 5th root of both sides. And when I take that 5th root on both sides, I'm going to end up with x equals 2.